This idea originated from Rutherford's gold foil experiment in 1911. Alpha particles helium nuclei were fired at a thin sheet of gold. Most passed through, but some deflected, and a few even bounced back. This led to the conclusion that atoms are mostly empty, with a tiny nucleus containing most of the mass. However, modern experiments with electron scattering reveal that atomic space is not empty, but filled with dense wave functions, which are difficult to interpret using classical physics. Quantum mechanics and the nature of electrons. Modern physics explains that electrons are not points but quantum objects, existing as both waves and particles. This was confirmed by the double-slit experiment, which showed that electrons exhibit wave-like behavior, interfering with themselves. Even when passing through the slits one at a time, they still formed an interference pattern, proving that they exist as a probability wave. In atoms, these probability waves form orbitals regions where the electron is most likely to be found. The shape of an orbital depends on the electron's energy. For instance, s orbitals are spherical, while p orbitals resemble dumbbells. Experiments confirming the lack of void. X-ray scattering. In X-ray crystallography, scientists use X-rays to study atomic structures. As the rays pass through a material, they scatter off electron clouds. The density of scattering reveals the arrangement of electrons, proving that atomic space is filled with complex structures. Electron capture experiments. These experiments measure the energy released when an electron is captured by the nucleus. The data show that electrons are not fixed at specific distances, but are distributed as waves around the nucleus. Scanning tunneling microscope. This tool allows scientists to see electrons on the surface of atoms. It confirms that electrons are not localized at a single point, but form a probability cloud around the nucleus. Why doesn't the electron fall into the nucleus? Heisenberg's uncertainty principle explains why electrons cannot be trapped in the nucleus. If an electron were inside the nucleus, its position would be known with high precision, and its momentum would have to be infinite, which is physically impossible. Additionally, Schrodinger's equation predicts stable wave states where electrons exist around the nucleus. These states ensure the stability of atoms and explain their long-term existence. Quantum technologies and the future of science. Understanding the quantum nature of matter has led to key technologies. Quantum computers use superposition to solve complex problems. Electron microscopes allow us to study objects at the atomic level. New materials. Quantum effects help develop next-generation superconductors and semiconductors. Rethinking the atom. Atoms are not empty structures. They are filled with electron clouds that form complex and stable systems. Modern science reveals a stunning quantum reality that underlies everything around us.